All right, welcome back for some more prob and stats. So today I'm going to try to keep it a little shorter than I've had the videos go in the past. We're talking about the least squares regression line. So let's just go ahead and get right into it. Okay, slides will cover all of what you need to know. So first of all, here's our two objectives for the day. Okay, we're going to calculate the equation of a least squares regression line using technology, as well as just manually doing it. But as you will find, manually doing it is pretty difficult if you don't have any of the data. All right. And number two, describe how outliers affect the least squares regression line. So this is kind of following in line with what we talked about last time, our regression lines in general. So hopefully you watched that. Now, if you didn't watch that, here's what you need to have known. Okay. Here's what you need to know going into the lesson here. You gotta know how to define these terms. If they don't mean anything to you right now, I suggest you pause the video and go watch the previous lesson. Okay. Regression line, residual, extrapolation. Okay, those are things that we need to kind of use to analyze our regression lines here. Second, predicting trends using a regression line. That was an objective from last time as well, and it will definitely help when we talk about the outliers later today. And finally, interpret the y-intercept and slope of a regression line. This will be very useful for when we actually do some calculation by hand. So it's very nice to have kind of sitting around in your knowledge of the brain here. Okay. Today, we're talking about the least squares regression line. So if you don't really know what that is, this is basically the standard regression line that a calculator spits out for you. It's the line that makes the sum of the squared residuals as small as possible. Okay, so in other words, it's where all of these little distances that you see here, okay, are minimized. We can also call this usually a best fit line. Okay. But either way, it is still a line at the end of the day, so obviously you're not going to have all these points connected in one straight thing. They are all on different little paths. Okay. But we're trying to minimize the distance between this line and the individual points themselves. Okay. That's what this little graphic indicates. Okay, so calculating by hand. Now this part is pretty lengthy and probably a little complicated, so please pause the video whenever you feel like you need it. Okay, I have all the instructions here, okay, to do it, but we're going to do it a little step by step. I'll have you, try it on your own as well with the Edpuzzle. So first of all, when we talk about the least squares regression line, we're obviously talking about a line. Okay, we're talking about this y equals ax plus b stuff. All right, so in that scenario, that's pretty simple. I think we all know how the lines work in, in math. We've seen them a bunch. Okay, they're kind of like an algebra 1 topic, even pre-algebra if you want to talk about that. But all these pieces A and B are found using some different parts of the data. So A, which is our slope, remember, is calculated using standard deviation and the correlation of your data, where standard deviation of the y variable, the response variable, is in the top, and the x, the explanatory, is in the bottom. Okay. R, of course, meaning correlation. Can be positive or negative, but it's always between -1 and 1. Next, we have B, which is calculated using the mean, okay, and this A from before, where we take the mean of the y, the response variable, subtract it from A times the mean of x. Okay. All right, and if you put it all together, you kind of a math whiz, you don't get lost in your work. Here's what it would look like if you tried to put it all together, where here's ax plus b, that whole nasty thing. Okay. Now, this is quite complicated looking. Okay. But so I recommend taking it one variable at a time. So just doing it one at a time. Here's A, find A, and once you're done with A, then move on to B. Once you find B, you just take those numbers you got and pop them back into the formula. All right, let's do an example here. So here's an example from the book talking about the January stock market. Okay. Some people think that the behavior of the stock market in January predicts the behavior for the rest of the year. Okay, so we already have our keyword here, predicts. Okay, so you'll definitely want to be thinking about that in terms of regression, which will help us do that. Take the explanatory variable x to the percent change in a stock market index in January, and the response variable y to be the change in the index for the year. Okay. We expect a positive correlation between x and y because the change during January contributes to the full year's change. Okay. Calculation from data for an 18-year period gives the following parameters. Find the equation of the least squares line for predicting full year change from January change and show your work. Okay, so typically this is how these problems will go. When we ask you to manually calculate it, we will be giving you all of these information. Where this x with a bar over it is the mean for the x values, which is this January change. The sx is standard deviation here, same thing for y and sy, and finally r is your correlation. So if you know all of those things, you should have an easy time just plugging it into what we've given you here. So let's get to the very first problem. Let's start by finding A. Okay, so that would be this guy right here. All right, and I'm going to give you a few minutes to do that. Once you finish, you can go ahead and continue the video. Okay, hopefully you got a chance to check your answer there. Here is the answer in the slides, 1.707. If you round it a little differently, that is totally fine. Hopefully the percent signs didn't confuse you here. Those are just units this time around. So we're not actually caring about turning it into a decimal or anything. So if your decimals were off because you're trying to mess with the percents, no big deal. Just remember that this is a unit. All of these have percent. So it's okay if we don't mess with the decimal translation of that. Alrighty. Next up, let's find B. I'm going to give you a few minutes to do this one too. Alright, hopefully you checked your answer on that one. But here is the answer, 6.083. Okay, again, note the percents are units, so we hopefully don't need to mess with that. That's taken from this B formula where I took the means, subtracted, and multiplied that second mean, the x bar, by what I got for A, that 1.707. Okay, so finally, if you got the A and the B, hopefully you can plop them into that formula at the top here. So I'll give you another second to try that out. Okay, and here's what it should look like at the end there. 1.707x plus 6.083. And this y is supposed to have the little hat, okay, the little hat for regression. Of course, I don't have a way of typing that here, so you'll have to bear with me on that one. Y hat equals 1.707x plus 6.083. All right, so if you found that very complicated and you got a little frustrated doing the work by hand, okay, that is to be expected because just like with some of our most complicated calculations, this is easier to let a program or calculator do the work for you. Okay, and I've compiled a couple of resources here for you that might help you on the homework and stuff like that. Here is this is a resource from our sampling. Okay, we can click on it and it'll take us to a place where we can put in our variables. Okay. Here's that social statistics one that I kind of showcased for the correlation. This is the first hit when you search for calculators online, but it works basically the same. You put in any of your variables, and you kind of determine what's x, what's y. Once you put them all in, it'll actually calculate the whole line for you. Finally, if you have a graphing calculator like a TI-84, you can actually use that, and it's actually really, really simple. So if you have questions about that, please let me know so you can, be quicker at this. Okay, not spending a whole lot of time, messing with least squares regression there. Okay. Finally, or not final, sorry, we got to get to the example here. My bad. So here's an example from the book again. I've got like two variables here, screen size and price of TVs here. Okay. I want you to go to one of those sites from the last page. Okay. You might have to go back, pause, and look it up. Okay, or you can try to find it by searching Google, or if you have a calculator, you can use that. Just plop these into your lists and see what you get. Okay, and here's what I ended up getting here when I plugged it into my little calculator. Okay, should be y hat equals negative 575.23 plus 25.11x. They kind of switch the two things around. Okay. I think typically you want to have this part up front since that matches our ax plus b form, but it's okay if you mix them around. All right. If you did not get this, you may want to check what you plugged in to your data. Okay. I think if you plugged it in correctly, you should get something similar to this, okay, assuming you did plug it in all correctly. All right, and finally, we got to talk about outliers one more time. Okay. It seems to get a pattern if I talk a lot about outliers. So in this regression line, you can see right here the red, okay, is modeled on this data where there are a bunch of dots over here clustered together, and child 18 and 19 are outliers in our graph. So when you take a look at this regression line includes both of these in the data used to get the line. Okay. But if you look at a graph where we cut out the pieces, okay, that blue line is a line of regression that would not include child 18, and the red one would be not including 19. Okay. So typically, if you have outliers in your data, they're going to pull the regression line towards their position on the graph. We know that this happens because our line is calculated using mean and standard deviation, and from before, you should know that those two things are not resistant. I'm going to keep saying it over and over again. Those two things are not resistant. So every time you see outliers in our data here, they're going to affect our line and the equation of the line, okay, ever so slightly. Ever so slightly. Okay. Just think about what it would do to your line's equation. Okay. If you're considering this blue line right here, okay, maybe describe how it moves compared to the green original line, okay, in terms of the y-intercept and the slope. All right, and if you answered that the slope became slightly less, decreased, and the y-intercept also decreased because of 18, okay, then you'd be correct. Well, not including 18, I should say. Okay. If you're talking about including it with all my data, it's making it steeper and increasing the y-intercept. Okay. Kind of the same thing for child 19 as well. All right, that's everything I got for today. Like I said, I tried to keep it a little shorter, not to blow your brains out or anything. But it is kind of the same we've been talking about with a correlation and all that other good stuff this chapter, but we were expanding that to talk about our lines we mentioned last time. If you got any questions, make sure to come to class prepared to ask those questions, and I'll see you then.